All right, so welcome to MFANS' fifth technical meeting. Today we're still going through some R stuff. This is probably gonna be our last R meeting for a while, unless that's what people want. It will be, we're gonna go over the basics of building a model. So that's very exciting. Model, of course, meaning in here, we'll just, to explain what a model is, we'll do a little bit of paint. Okay, so really what modeling is we have some data on the x-axis, we have some data on the y-axis. And we have all of this data that's correlated in some way. Okay, well, we want to predict y based on x. So we want to build a model. Well, what is a model? Well, we fit a line to it. This line is the model. This guy right here. That's what the model is. So whenever someone says they have a model for something, that just means I have a line that I fit data to. It's really hard to figure out which type of line is best and what exactly should be in this X. So a very bare bones, what do models mean is just fitting a line to some data. What we'll cover here is probably the simplest simplest type of model, which is a linear regression. So regression is the process of fitting the data to not that guy, fitting the data with a line. So what all that is okay, we have some data y that we want to predict, and we have some input variables x. And the data in y looks something like this. And we take our x variable and we say, okay, well, let's try and predict it using a line. This is the simplest model that there is. You've done this multiple times in your algebra classes. In algebra 1, you fit a y equals mx plus b. So really all we're doing when we're building this model is we're using, the computer is going through these algorithms to find what's the best m and what's the best b. And then we have a bunch of tests to see how good it is. So let's get into how we do this with R. So generally with building models, there's a couple steps that you go through. One, it's actually getting the data. Two, it's wrangling the data. So that's what we did in one of the prior meetings. Basically, we found out what's the best way to get the data to look how we want it to look. And there's this EDA, exploratory data analysis. We see what the data looks like. We understand how things are correlated together. And then we actually train and fit the model. We'll be doing kind of a version of that. What we're going to do is we're going to use nflfastR again to try and predict win totals for next year. As I'm going through, I'll copy and paste the code chunks into the chat so that you guys can follow along, because I know it can be kind of hard to read just right off the screen. So here is actually, we're not going to be using these two packages. So here are the packages we'll be using. There's the chat. So those are the packages we'll be using, and this is the very first. And since we're going to be predicting win totals, so we'll use 2019 and prior data to predict 2020 win totals. We're into the season already, so a little late in the process, but it will actually be able to evaluate a little better based off of that. So we can find out what team and what season has won how many games, but that's really annoying to do all that data wrangling and with nflfastR data. So what we'll do is we'll just read in this file from Lee Sharp. He's this guy on Twitter who does a lot of betting stuff. So we'll load in our packages like we always do. Oh, so we'll load in this file and then we'll see what it looks like by just doing games. Okay, so we have the game ID. This I'm pretty sure matches up with I think this might be a unique ID or it might match up with nflfastR. It won't matter, we're not merging based on this at all. The season, if it's a regular postseason game, the week, what day it is, the weekday, the game time. I don't know when we actually start having the game time data, probably around like 2007, 2006-ish. The away home team, their scores, what the result was. This is the away score minus, this is the home score minus the away score, the total, and yeah, some other betting data, and we're not really going to worry about the betting data. So and rest. So how much rest they had? Did they have a Sunday game the day before? We're not going to worry about that. But what we're worried about is the team and the result. So the first step of any modeling process is to, well, one, know what you want to predict. We want to predict win totals. Now we need to figure out, okay, what do we think goes into it? Well, just off the top of my head, score differential. There's this idea called Pythagorean wins, made by Bill James, I think. Basically, it's predicting wins based off the point differential. So if we can somehow, so we have information on the point differential of that team in prior years, maybe we can predict how many wins they'll get. Also, maybe EPA per play on offense and defense, and maybe passing and rushing. That seems like a good way to start. So how good your offense is, how many more points you score than your opponents, how good your offense is, how good your defense is, how good you are passing the ball, how good you are running the ball. That seems like a pretty good basis without considering who your opponents are, what your schedule is, who your quarterback is, if your quarterback, what year your quarterback's going into, your win totals for the prior year. Just as a real bare bones first swing of the bat of the model, this seems like a good place to start. So like always, we'll start by wrangling the data. So we're only looking at, so first we're going to take the regular season games, and then we're going to select the data we want from that. So the season, what year it is, the home team, because we group by home and away team. If we actually do that really quick. So we do games, group by home, rest, team, away team, and then we'll summarize just, I don't know, n times equals n. Okay, so now we see how many times the Cardinals have played the Falcons since 1999. How many times the Cardinals have played the Lions since 1999. We don't want that. We want it for each individual team for each individual season. So with the way this is structured, we actually have to group it by the home team and then by the away team. So by a home team, we'll just do this. So we'll filter just for regular season, because when you bet win totals, you bet on the regular season win total. We'll select the data we want. So the season, the week, the home team, and the result. So this is every game in every season for every home team. And then we want to rename. Renamed does exactly what it says on the package. It just renames the column to something else. So home team to team, we run that. And just to make sure it does what we think it does, home. So it gives us the season. Okay, so this gives us the result of, so we see that the Falcons in week 1, in 1999, week 1, they lost by 3 points because the home team lost by 3 points. Sick. Now we do basically the same thing with the away team. The only difference is we don't worry about the result. So actually it'd probably be expedient. Oh, so we take -1 times the result because we're worried about for an individual team. And since the convention here is home score minus away score, now we want to see away score minus home score. Oh, and so we just run that. Then I'll throw these in the chat. I watched back the playback of last time and I say, I'll throw this in the chat. It's funny. So here, now we look at away. Okay, so now we see, and if we look back up here, the first game in the data frame is Vikings at Falcons. So for the Falcons, that result is -3, but for the Vikings, because they're away team and they won by 3, the result is +3. Okay, cool. So now we have what we want, but now we have it in two separate data frames. How are we going to manage that? Well, what we learned previously is we can try and merge them, except that doesn't really make too much sense here, because if we say, let's say we merge on the season, then we just have what we have before. that'll just confuse it also. If we merge on the week, that'll confuse it. If we merge on the team, then it'll be like Vikings, 1999, 1998, 2000, just to show you what that looks like. So if we say merge home away by team, it'll take a moment because they're kind of big. But it'll look gross. So what we'll do instead is we'll do bind rows. So what that does is it binds the rows of one data frame. Yeah, see, this is disgusting. And we don't want this. So it just has repeated data. It has 26, it has the 2016 Cardinals with all of the other ones. And it's just really weird and gross. And that's not what we want. So we want to we'll take the home teams and we'll just we'll just kind of glue the away team to the bottom of it. So we'll bind the rows. So we'll use the bind rows function. So what this will do is we'll have 99 week 1 Vikings result +3. And then we'll have 99 week 1 Falcons result -3. So then we have the result for every team in every week in every season. So we'll bind those rows. And then to make it easier to read, we'll arrange by week. So we'll have all the week 1 games, week 2 games, et cetera, et cetera, et cetera. And then mutate. So now we're going to add another column, which is win. So now we'll see, okay, did this team win or did this team not win? Instead of doing case when, we could do something like when equals if else result is greater than 0, 1. So if the result is greater than 0, which means the score differential is in that team's favor, then yes, they did win, so they get a 1, or no, they got a 0, so it's a loss. However, there's a weird case here where if they tie, actually, they get half a win. So then we have to do something like, we have to take out that 0 and do if else result equals 0, double equals 0, 0.5, else 0. That means they just lost. But this is kind of gross, and this, I don't mind this really, but it's hard to read. So what we can do instead is we can use this case when function. So we'll see, okay, when, so we have our 3 cases, result is greater than 0, then we put a 1. R likes to use this tilde a lot, and I hate that it likes to use it, but it does. So it'll come up again later. But basically, it maps 1 onto this case. Then map 0 onto this case and 0.5 onto this case. So now if we run that, now what we get are results. So now what we see is, okay, so now we see in 1999, the Falcons lost by 3 and they did not win. Sick. And if we want to look for the ties really quickly, just to make sure that it worked, filter win equals 0.5. Let's see. Oh, we can actually see the Falcons, the Lions in week 1, along with the Cardinals in week 1, which is super fun. Steelers and Browns in 2018. So cool, works, great. And I'll throw this in the chat. I need to say something else, then I'll throw this in the chat. Okay, so now, so this is great, but since we want to bet total, hypothetically, we would like to bet totals off of this. Now what we want to do is we want to see for each team's season, because that's what we're worried about, right? So we want to bet how many games the Vikings will win in 2020. Joey wants to bet how many games the Falcons will win in 2020 because he likes to lose money. That's what we will look at. So what we're going to do is we're going to take this data frame up here. We're going to group it by the team and the season, and then we're going to summarize it. So in that group, we're going to see how many games did that team win. Awesome. So this will give us like 10, 12, whatever. Point differential, we're going to sum the results. So this will let us see how many more, what the point differential for that team was. So if they scored 100 more points than their opponents, it'll be 100. Because as we can see here, result is 3. So they scored 3 more points than their opponent. we can just sum those bad babies up, bad babies, bad boys. Sum those bad boys up, and then we get the point differential for the season, and then ungroup. I actually don't know if that does anything, but a lot of people do it, so it's safer too. You guys want to do that yourself? And now we can check just to make sure it does what we think it does. Not that. Teams wins. Oh, it's team wins, not teams wins. Yeah, so we can see, okay, the Cardinals in 1999 won 6 games that had a minus 137 point differential. That's really bad. Just for fun, let's see what the Lions did. Team that. Fun. Between 1999 and 2008, most games they won in the season was 9, and they never actually scored more points than their opponents. Just for fun. That's why we're looking at this. Okay, so now this has data we want. Cool, but like we said earlier, we want to look at EPA, because EPAs are really good to evaluate how good a team is, how good their offense and defense is, and particularly their running and passing. So we'll just load that data in with the same, but we're only going to look at the regular season data with this. We're going to filter out the not available plays like we did before. I don't know what this is. I guess that there's just some gross things in the data, probably for teams that move. So if there's any missing offensive teams, we'll remove that. If there's a blank slate in the offensive team, we'll remove that. So if it's run or a pass in the regular season and all the data doesn't look gross. And all we want is what season it is, the offense, if they passed, the defense, and the EPA for that play. So we'll just grab that and I'll paste that into the chat box. There we go. Okay, and while we're waiting for that, we need to go through some more data wrangling with this, because data wrangling is an extremely important part of building models, if super tedious and annoying and the least fun. It is probably the most important. And this will take a second because we're loading in 20 years of data. And I'm sharing this. So, okay, so we want to merge this with our other data frame. So we need to group it in similar ways. So but again, we can't group it by offense and defense at this. We can't group it by a single team's offense and a single team's defense. So we have to do the same kind of trick that we did before. So what we're going to do is we're going to look at the offense first. So we're going to group it by the possession team, so the team on offense, the season, and whether or not they pass. And then we'll get the EPA per play of that offense running and passing. And this pivot wider, I'll explain in a moment, but this is really because it looks kind of gross. So we're going to fix that. And then we're going to rename this column. And then we're going to rename this again. So because we're grouping, okay, so I should have loaded this data frame before. So basically what this is doing here. So what this is actually going to look like is it's going to have a column. It's going to have a column with the season, with the team, with the EPA per play, and whether or not it was a run or pass. So we're going to have 2 rows for one team in one season. We don't want that. We actually want 1 row for a team in the season. So what we do actually is we're just going to take the EPA per pass, and just going to take the pass row 0 or 1 is did they pass or not, and then we're just going to move that up with this pivot wider. So we're going to grab 2 columns, and they're going to pivot it. And here, and actually demonstrate that right now. So I'm just going to comment this out for a moment. Okay, so we can do that. So here's what we have in offense right now. Offense. So here's what we have. So see, we have the Cardinals in 1999. So when they ran the ball, passes equals 0, they had an EPA per play of minus 0.2. That's bad. But when they passed the ball, they had a EPA per play of minus 0.16. Still bad. but better. But also, this isn't what we want the data to look like. What we want is we want this. So we want this. So we want their EPA per run and their EPA per pass to go right next to each other. So we just have Cardinals 1999 minus 0.2 minus 0.162. So how do we do that? That's where this pivot wider function comes in. Oh, and also the comment out data with the, that's what this little hashtag does. It's Control-Shift-C. We can just do Shift-3 to get the hashtag. So now this pivot wider. So we need to say, okay, so we need to specify what these columns are going to be named and where we want the values from. So we're going to get it from here. We're going to get the names from pass, so 0 or 1, and then we're going to get the values from EPA, so the EPA per Russian pass. So we run that really quick. And there we go. So now we have the Cardinals. This is their EPA per rush, and this is their EPA per pass. But if you see here, because we got the names from the pass column, it's 0 or 1, and that's a gross name. So we're going to fix that with the rename function. And now it's nice and pretty. See, EPA per rush, EPA per pass. And we do the exact same exercise with the defenses. I'm not going to go through it like at the 6th time, but same idea. Okay, so now we want to. Okay, so now just to check, well, we have the team wins. Okay. I don't know why I included this. We don't really need that. Okay, so now now we're very close to being able to merge these data frames. The only issue, of course, is that the Chargers, Rams, and Raiders all decided to move on us and change the name conventions. So we just have to fix that really quick. We're going to use the case when again, just because it's gross otherwise. So if the team is Oakland, Las Vegas, San Diego Chargers, Rams, LA Rams. Let's run that really quick. Again, this is just to make it so when we merge, it works. So now we have the offense, and we have the defenses, and we have the team wins, exactly how we want it. Now we just need to kind of smush all these together. So how are we going to do this? Well, first we're going to take the team wins, and we're going to, so we have our team wins, and from the left, so we're going to keep all the team wins, and then we're going to merge the offenses onto that. And then we're going to take this, and my third hand, which is my head, and we're just going to smush it on. Then we're going to take the defenses and smush it onto the offenses and the team wins. So to do that, so we'll take the team wins, and then we'll left join it by the offense. And I actually don't know why that argument is. Yeah, that's why. So then we're going to say, okay, we're going to take the team, and it's named pause team in the offensive frame, and then we're going to also look at the season, and I'm going to smush those. And then we're going to do the same thing with the defense, except it has a different name. And now we have now we have all the data we want. And we're going to choose a very creative name for that, which is data. So, okay, but now we still want to look at, so now we have it for a given season. But if we're trying to predict the next season's data, the next season's win total, we're not going to be able to bet win totals after we know how many games the team has won, unless this is a Martin McFly situation, in which case, why are you here? So we have to get the last year's information. So the way we do this is with the lag function. The lag function basically goes to a column, goes to a row, and gets the previous row's data into that column, into that row, which is very, very useful. So prior off rush EPA. So what it's going to do is for the 2000 Cardinals, it'll take the offensive rush EPA and put it right there into the void. So to explain what I mean, okay, so we see right here. So we see the 2000 Cardinals have this data, and we see that the 1999 Cardinals have -0.2 EPA per rush and 0.16 EPA per pass. So arrange that we don't need to arrange, just to keep it in the same order.
So Connor,
What's up?
oh, sorry, I didn't mean to cut you off.
You're good.
So do you have to put the arrange when you're using the lag function?
Yeah, yeah, that's it.
Okay.
Yeah.
Or else it wouldn't know like which one to, or would it just like get the row above it if it was just like randomly
Yeah, it would
ordered?
just get, yeah. Like,
Oh, okay, that makes sense.
I
Okay.
think it still has the order right now, but if there was like Cardinals 1999, Falcons 2018, Cardinals
Mhm.
2001, 2001 would take the Falcons in 2019, and that's not what we want. So that's why we arrange. A good point.
Okay, thanks.
And here we go. So we see that the Cardinals in 2000 have a prior rush EPA of, so prior rush EPA is negative 0.2, which is right there, and a prior pass EPA of negative 0.16, which is right there. So good, does what we think it does. Okay, so now we're about to build a model. So now we have to consider, okay, do we want all of these in the model? And we also want to see how predictive are the things that we think are predictive. So what we're going to do is we're just going to take a little snapshot. We're going to select everything besides the team and the season, so so it doesn't affect our data at all. So we don't see, okay, the Cardinals wins are especially more predictive as opposed to the Falcons wins. We're not going to assume that. That would be a bad assumption to make. I'm hoping for obvious reasons. Also, we're not going to see how well 1999 correlates with 2000 with the season, because that'd be dumb. So we're going to select those out. So we keep, so to deselect things with a minus sign in front of them. I'm pretty sure we covered this. And then we're going to use the core function and this use complete.obs. That just gives you, I'm assuming you've at least familiar with an R squared. R squared tells you what % of variation in one axis is explained by another. So how much? So if y deviates by this much on average, how much is explained by this much deviation in the x-axis? Basically, how good is the line? And then we're going to round it so we don't get massive annoying things. Did I throw the? Oh no, I also need to throw this in the chat. Okay. So we're going to run this really quick. Okay. So here, I'm just going to expand this a little bit so we can look a little closer. Okay, so here we can see that, okay, so wins. So this is a little much. It would be better to make a visual for this, but since it's just us in the background, we can do quick and dirty stuff like this. That sounded bad. So we can see how well different things correlate with each other. So we can see how well wins correlate with wins. Good, they correlate perfectly, just like we would hope so. And in a given season, a point differential actually correlates extreme. So also this correlation goes from 0 to 1. 1 being it makes a perfect straight line, 0 meaning there's absolutely no correlation and it just looks like a cloud of dots. This is a cloud of dots. So we see, okay, how well do these things correlate with each other? Okay, so a team's point differential with wins, their point differential is extremely well correlated with their win total, as is their passing EPA, much better than rushing EPA, which makes sense. The passing game is more important because it's generally more impactful because it has a higher EPA, because you gain more yards, because it's easier to defend a run than a pass. Yeah, it is easier. That's yeah. And we can actually see that defenses on the whole are generally less predictive of wins than offenses. Well, this is interesting by itself. This suggests, oh, maybe you'd rather have the number 1 offense than the number 1 defense. That's interesting. And now, okay, and this is the stuff we're going to build our model off of, so that the prior rush, so the team's rushing success last year isn't, so we wouldn't also, first off, we wouldn't expect any of these to be particularly insightful on their own, right? Like you wouldn't just, because it's so far removed from everything else, you wouldn't expect to say, okay, this team was this good at running the ball last year, so they're going to win 12 games. That's not how football works. It's a little more complicated than that. So we wouldn't expect individually for them to be particularly predictive on their own. But we can see of these that the prior point differential is is really predictive, and that rushing and passing EPA are more predictive than defense. So it might not be, which isn't very predictive at all. Oh, the negative, quickly explain the correlation. So positive just means you have a positive correlation. So high X means high Y. Negative means you have a negative correlation. So low X means high Y. So low, high, so on. Hopefully that shows up in the recording the right way. It's not reversed. That'd be unfortunate. So yeah, and also in here we can see any collinearities. So like if we go to point differential is really well correlated with passing EPA. So we might worry that if we include these things together, it might make our model a little less accurate with how they work. But for our purposes, we're not going to really worry about that too much. Although it would be best practice that if we pick one it wouldn't be good to do prior passing EPA and prior point differential. If we go over here, so we go to prior pass EPA and prior point differential, they have a really high correlation. So 0.76. So that means one, they have collinearities, which messes up the algorithm for how you get correlations. They have to be independent. If they're really well correlated, they're probably not independent. And also, it tells us that gives us basically the same information. And we wouldn't want redundant information in our model just because that also affects accuracy, I think. Also, just it's better to make things as simple as possible from a pragmatic explaining things standpoint, and just having a bunch of redundant information, even if it increases accuracy, isn't worth the extra hassle of, oh yeah, I have this model and I have 8 ways how efficient something was. So if we want to include point differential and passing EPA, we'd probably want to pick one or the other. And since point differential is more predictive of wins than prior passing EPA, we'd probably rather pick just the point differential. Okay. Yeah. So now we have insights, and now we can take a step to go about making a model. But then let's take a quick second. We have 20 years of data that we have right now. The NFL has changed quite a bit in the last 20 years. Sean Alexander won the MVP in like 2006. Adrian Peterson won the MVP in 2012. The NFL has changed a lot in a very short period of time. So maybe it's not the best thing in the world to use 20 years of data. So let's just look in the past decade. Let's just look since 2009. Let's see if that gives us any different results. Oh, and we're only going to look at wins, point differential, and so we see from here that defense isn't super great to include, so we're just going to ignore it. Throw defense out the window. Defense doesn't matter. So instead is we're just point differential and the various and their prior versions. Okay, so now we look down here, and this is just from 2009, so this is more recent NFL data, so we would expect it to be more accurate. So we look at wins, point differential, still super predictive, passing EPA, still super predictive, and actually we see that point differential and passing EPA are more predictive than they were over the whole data set. So it's 0.43 since 2009 versus 0.36 over the whole time, 0.34 for passing, 0.29 over the whole time, while actually rushing is about the same, which is kind of cool. I don't have any analysis to tell you. I just think that's kind of cool. But the prior point differential and the prior passing EPA is still really well correlated with 0.78, extremely well correlated. So we one of those. So that means teams are getting better at passing the ball. So sick. And since this data, we would believe it's more relevant and it's more correlated, over this time period than the whole data frame, we're only going to look at, we're only going to train this off the past decade of data. I need to throw this in the, is there a way to arrange these strongest correlation comparison? I'm sure there is, just, yeah, that would have been a good thing to put there. I actually don't, yeah, also I throw that in the, I'm gonna put this in the chat really quick. Yeah, there is. I didn't prep that, and I'm actually not sure. This is usually what I do when I build my stuff, so I don't really. Yeah. There is. I should have prepped it. My bad. Left to the reader. If I find something up in the description of the video. Okay. Cool. So how about? Okay, so let's just build a really naive model just for fun, just to see what it looks like to kind of ground. This will act as our baseline. Okay, so we have the passing and rushing EPA for offense and for defense. We know point differential is better, and an optimal model might have just rushing EPA and point differential with our data set. But let's just set a baseline. Let's include all the different EPAs from the prior year. And also it is general best practice to avoid overfitting something. So what overfitting means, if we return to paint really quick. So if we just, can we clear this? Clear it. Okay, so just to really quickly explain overfitting. So overfitting is if we have, say, data that's like this, right? We want our line to go like that, like shoot the middle of it. What overfitting does is overfitting says, okay, and just plays connect the dots, which obviously you can't predict off of that. So we avoid that by splitting our data sets into training sets and testing sets. So I don't have that code prep offhand. I should have done that. So general best practice is to split this up into training and, wait, is it sample? Oh, also, fun little thing in R. In R Studio, you can do question mark and just the name of a function, and it'll tell you what it does, like I just did with the sample. Oh yeah, cool. Okay, so here's what we do. So we do, so we'll just call this end. So we're going to sample. We're going to sample our data with C. So C creates a vector. So we're going to sample at 80% one, 20% the other. 0.8 and 0.2. And we look at end. Yeah, so it has those two. So now we're going to go to our testing set. So our training set. So the training set, this is the bigger set of data. And with the training set, is the dots you have to make the line off of. So we're going to do data end equals 0 or end equals 1. And then we're going to do testing. So the test is, okay, I built this. Now let's see how well it works. Data. Is a matrix. Set the same dimensions as the input. It gives me. Tage, do you know how to do what I'm trying to do? Do you remember?
I'm looking at it, but I don't know. Okay. I don't know why it's giving that problem.
Okay, so little inside baseball. When I make my models, I have some code I've copied and pasted from Stack Overflow, and I haven't touched it since I first copy pasted it. So I actually don't remember. So general best practice, I'll put the code in the description of the video, and I'll send it in the GroupMe later. So general best practice is to actually split your data into training and test sets. For these purposes, for explanatory purposes of how to build a model, we're going to not do that because I'm an idiot. I didn't prep well enough. So just keep in mind that we are at risk of overfitting our data right now. But this will go through how mechanically do we make a model. Again, I'll send the GroupMe later, and I'll have in the description of the video how you actually take a sample set. So I'm just going to delete those. Okay, so now we have our data, we have our points, and now we want to connect a line to these points. So this is how we do it. So R just has this built in. It's called LM or GLM. GLM is, so there's linear model or it's generalized linear model. So what that means is, remember, a model is just fitting a line to some data, and GLM is multiple ways in which you can fit a straight line to this data. So our target variable, that's what we want to predict. So we want to predict wins. And we're going to do this. So we have our target variable, and then we have our squiggly, our tilde, input variables. So we are going to predict our target variable with our input variables. Target variable goes on the left of the tilde, input variables go on the right of the tilde. So we're going to predict if the prior EPA information, our data set that we're using is data. Optimally, this is a training data set, which I'll send in the GroupMe or in the description of the video later. That's the line of code. So, okay, so cool, we have this. Is it good? Well, let's see. So this summary, this just summarizes what it does. Summarizes the data frame. So the residuals, the residual is also in some of your science classes and your physics, this is just the error. So the distance between your estimated point. So the residual is the distance between a given point and the predicted point on the line. So our minimum residual is that, our max is that. So we're off at most by 7, most of the time by 0.1. That's a little misleading because this is a metric data set. Don't worry too much about the deviance residuals because of that fact, but this is really what we want to look at. So what are each of these? The estimate, what we think that M is, the standard error, the deviance of the error between what that weight is for each point, the t value, and the probability of t. Outside the scope of this to explain in full what those are, but basically this is the p value. This is the probability that this is just due to random chance. You generally want this to be below 0.01 is usually acceptable, and we've crossed that threshold except for the defensive, which makes sense. Defensive is generally a lot more variant, but it's still lower than 0.1. So there's a 1% chance that this is due to the variance and a 4% chance. So there's a 1% chance that the impact of last year's rushing defense is due to chance. And there's about 4% chance that last year's passing defense that weight is due to chance. So, okay, that seems pretty good. And keep in mind these residuals a little bit. So at most 7 usually, so at most we're about 7 to 8 games off, which is significant. But most of the time, the middle of 50% of the time, we're about 2 games. So third quartile, so 75% of the time, and one quartile, 25% of the time, we're between 1 and 2 games off. 1 less and 2 more. So about 2 games off, either way. Okay, so how does just last year's point differential do in comparison? It is significant. That's what means when the point value is low. But actually, interestingly, the residuals are about the same. So it looks like it doesn't really matter. So, okay, cool. Now we want to predict next year's data frame. We want to predict 2020's, so this year, 2020's wins. Okay, so how do we do this? Well, okay, so this is predict function. It predicts data. So you have to specify the model you're using. So we're going to use the first fit model. And the data we want, so we want data, but only from the 2020 season. And then this is, so this just gives us the, so this is just some, oh, actually I should copy and paste this. So you actually need to make this a data frame for this to work. Right now, okay, so we just do data filter 2020. Oh wait, that's an extra. Yeah, right now it's kind of weird, and it's not the shape we need it to be. So we need to make it a. Yes, we need to make it a tibble, which is just a data frame. Not super important. If you structure this the right way, if in your own practice you structure it the right way, you generally won't have to worry about this part. And then we rename the prediction to value. I don't know why they do this. Round one, so we're going to have one decimal, and then we bind the columns. So we take the column that we're predicting, and we merge it onto the whole data frame. We merge it onto this. And so we run this. And I'll throw that in the chat. And let's see what our predictions are. Okay, cool. So we predict that the Cardinals in 2020 will win 8 games. The Ravens will win 11. The Bills will win 8. Cowboys will win 10. Rip Cowboys. Just for fun, we'll look at the Lions. Filter. Yeah, so they project the Lions to win 7 games. How do you feel about that projection, Tej?
Not great.
So, okay.
So wait, so that's weird that it's still 7 even though Stafford was out half of 2019.
Yeah. So
yeah,
so you want to consider here, maybe Stafford's coming back, so we maybe think it might be better. This is a very rudimentary model. Okay, so we know how this looks. Feels all right. So it's definitely low on the Bills. It feels like a little low on the Browns, maybe high on the Bengals. So we know that the Giants and Jets are bad, so let's just look at the Jets. Sorry, John. Maybe high on the Jets. Giants at 7. Yeah, Giants at 7. Which also a little high. I guess they thought Daniel Jones would be not bad, which he is. Okay, so now this is cool, but we have another model. So let's just play comparison. So let's do the exact same thing, but with fit 2 this time. So this is just based off last year's point differential, which according to our summary statistics from last time should be about the same. So we shouldn't expect too much deviance between the two. So Preds 2. And if we just do a quick look, Ravens 11.2, this had 11.4, Bills 8.7, Bills 8.2. So they seem to line up generally pretty well. Let's look at the lines again. What? No. Why are you mad at me? Oh, team equals that's why. 6.9, nice. Also had them 6.9. Jets 6.9. So this one's 0.1 wins higher than the Jets. Higher on the Jets. The Giants 6.6. So yeah, so we have a model. We've tested it with some intuition more so. The only really testing we went through with this one to see, okay, does this make sense, is we looked at the summary statistics. So we know it's not crazy accurate, but most of the time it's plus or minus 2, which is pretty decent for this kind of model. On the season level, totals are kind of difficult to beat. But plus or minus 2 is a really strong start. For the first swing of the bat of the model, getting within like 2 wins on 50% of the time is really good. So just to review, so we've wrangled the data to get it how we look. We've merged it in various ways. We've done some exploratory testing by looking at correlations. It would have been better to go through and look at the shape of the data, but that's kind of redundant for this data frame in particular, because we're looking at something done by humans where some are clearly better than others. So we get a lot of just normal curves, and that gets boring really quickly. And we can just suppose that they're normal. Maybe you can't publish a paper by just supposing they're normal, but for your own purposes, and then we fit some data, and then we ran with it. And actually, we can use really quick what we did earlier, what we learned earlier, and say, okay, how about we just look at point differential and how good their rushing offense was, and we can see if that's any better. Prior, was it rush EPA? Or yeah, prior off rush EPA. Okay, and let's see how that does. Not much better. Oh, and actually, it's useless to include this because it's not significant. So we can't differentiate if any improvement on this model is done by the rushing EPA or just random noise, because there's a 30% chance that the improvement by rushing EPA from last year's offense is just random. So yeah, that's really basic how to build models. Basically, you wrangle data, you explore to see what the data looks like. If you're not sure what it looks like, then you see how well different things are correlated, and then you test it. So yeah, and then you just iterate that process more so. There's more advanced modeling techniques. There's different lines you can fit. Like a big one is if it's 0-1s, it's a logistic model. But the general flow of how we build models is we get the data, we get the raw data, we wrangle it, we get it to look how we want. Then we explore it to see what the different variables look like, see how well they're correlated with each other, and then we test it. And testing it is, a lot of it is just kind of feel, not a lot of it. There are some more rigorous statistical tests you can go through. Like you can look at R squares and you can look at the residuals. A lot more of it's feel like, okay, it said the lines were at about 7 preseason. That feels about right. At least with respect to sports. Anything else, gotta be a little more rigorous. But so yeah, that's how you build. Crash course and how to build models. We can go into further depth if there's a market, if you guys want to. So yeah, any last minute questions before we head out? All right. So